Well, this is the first time that we've had Dr. Ragozzine with us, and it should be an interesting talk tonight. And thank you for everybody that's joining us on Zoom and YouTube, or the two people that are joining us on Zoom tonight, because apparently the links weren't working correctly. So if you found us over on YouTube, we appreciate it. And, you know, give it a like over there. Yeah, of course, we're on, as I mentioned before, that we're on YouTube and Facebook and X and Mastodon and Instagram. I don't know. We're on all sorts of stuff. So you can find us out there, right? You can find us out there at any time. But Dr. Darin Ragozzine is an associate professor at Brigham Young University in Utah. And after a physics and astronomy and astrophysics double major at Harvard, he completed a PhD at Caltech in planetary science in 2009. He's been an active researcher in the orbits of planets for 15 years and has co-authored and has authored nearly 100 publications with over 10,000 citations. Now, BYU awarded him with a Junior Faculty Research Excellence Award, given to only 1% of the faculty, and was also awarded the highly competitive Early Career Grant from the National Science Foundation. He's an expert in both exoplanets orbiting other stars and small bodies orbiting within our own solar system. So please welcome, for the very first time from BYU and way out in Utah, Dr. Darin Ragozzine. Welcome, Doctor.
Hello. Hello, everyone. I appreciate that very nice introduction. Would you like me to go ahead and get started on the presentation then, or?
Yeah, how do you feel about taking questions, and where you want to do Q&A at the end, or how would you like to do that?
Oh, I'd love to have questions as we go, especially if there are things that I can help clarify, make sure everybody's kind of following along with the discussion. So you're welcome to ask questions at any time. And I was under the impression that someone would be kind of moderating the questions and passing them along to me. Does that work for you?
Yeah, the only thing is that our Zoom links, there's not very many people in Zoom. They're mostly over on YouTube. So I'll be trying to keep an eye on both. And anybody that asks questions, you know, I'll try and pass them along to you, and we'll just kind of keep it going. But, you know, for the most part, just plow through it. And, you know, as questions come up, I'll throw in there and try and define down, you know, maybe, you know, some of the things that you're talking about.
Sure. That sounds great. Well, thank you. It's a pleasure to be here with the WAS, the Westport Astronomical Society tonight. I'm glad to be talking about some things to people who are really interested in, you know, astronomy and the types of things that we can learn about them. And I'm Darin Ragozzine. As was mentioned, I'm a professor at Brigham Young University here in Utah, and I work on orbits. You know, when we discover these objects, one of the first things we learn about an object is how it goes around the sun. Sometimes we study planets around other stars. The first thing basically we learn about that is how it goes around its other star. There are many objects that we don't really know how big they are, or how heavy they are, or if they have moons, or what color they are, or what shape they are. We don't know anything about them, but we know how they orbit. And so, you know, following these orbits really allows us to, you know, use a lot of information that we've gathered to try to learn more about the solar system, about the universe around us. So I'm going to kind of have three. It's a little bit of an indirect path, but I have three major topics we're going to be talking about. The objects that I'm interested in talking about today are out beyond Neptune. So we're used to the asteroid belt between Mars and Jupiter, but this is another belt that's out beyond Neptune, the Kuiper Belt, filled with icy objects. So I'll be talking about that, kind of introducing that. And then I'll also be talking about what we call binaries. This is two objects. So there will be two objects, two ice balls out there orbiting each other as they both orbit around the sun. We'll talk about that. And kind of a thread through that discussion will also be how did our planets form? How did the planets in the solar system, how did they get put together? Why are there asteroids and Kuiper Belt objects? What's going on? And then at the end, I'll kind of introduce some of the research that I've been doing recently, working on right now, getting the paper drafts ready to send over to a astronomical journal to publish. And it's about measuring the shapes of these objects as they measuring the shapes of the objects that are going around. And we'll talk about how that's possible, even though I can't see them at that time. So I thought I would kind of start with this idea of planet formation, because you know, a lot of times in science, what we're trying to do is we're trying to figure out a key scientific question of great interest. And one of them is, how did our solar system form? And the short answer is you start with a big cloud of gas and dust, and then gravity starts to take over and brings that cloud of gas and dust together. And it's spinning, and as it shrinks, it spins faster and faster, and that spreads it out into this disk. And thankfully for us, it takes time. It takes a couple million years before most of the material in the disk ends up in the sun. And during that time, things can start to stick together and grow and become larger objects. And so, and leaves us with a little bit of debris out here that we live on, out left over and that didn't end up in the sun. And so, but now, you know, if we want to start to ask details about this process of like, well, how do you start out with dust, which is, you know, really, really fine. How do you end up with something really fine and then end up with something the size of an asteroid or a planet? How do you do that? And that's kind of one of the key questions for us. So how do planets form? And what we have learned, both in our solar system and in other solar systems, now the dominant hypothesis for how planets like the Earth and Jupiter, all the planets in the solar system, how they formed, is that they don't form all at once. You don't start with a big, so unlike the star, which kind of forms all at once, right? You start this big gas cloud and it kind of collapses, and then you make the sun. That doesn't happen for Saturn or Venus. You don't start with a big pile of little dust particles and now all of a sudden you have a planet. There's an intermediate step, a step in between that. And we call the pieces that go into planets, these pieces, we call them planetesimals. And planetesimals are your everyday asteroids and Kuiper Belt objects. These are planetesimals, you know, little baby planets, right? Before you can make a planet, before you make the Earth, you make a bajillion asteroids, and then, you know, the asteroids then start to come together, and then that forms here. So you start with little pieces of dust, and then bigger, and then take a couple of those big ones, make it bigger and bigger and bigger, and you go all the way up to a planet. That's how we think planets form. But in a second, I'm going to show you that this story doesn't quite work for planetesimals as when we start really thinking about it. But if we want to answer this question about how did these objects form, well, it makes sense to think about, well, what can I measure? What can I go out? What picture can I take? What can I gather to really learn more about how these planetesimals form, right? What can we do? And, you know, what's within our budget too, right? Because, you know, it'd be nice to go out and mine some asteroids and crack them open and look what's on the inside, but that's not in our budget yet. So, you know, with what we've got, what can we do to sort of figure out how these planetesimals form? And what I'm going to tell you about today is that there's a population out in the outer part of the solar system beyond Neptune that's basically in deep freeze. This population formed, the planetesimals formed, and then nothing has happened to them for 4 billion years until today. And if you want to figure out how something happened, you know, looking at the best evidence, the most earliest thing, that's a really great way to do it. And as we look at these objects, what are we going to, you know, so if I say, okay, this is a pristine, you know, planetesimal formed right out of the solar system, what do you want to know about it? Well, everything, right? I want to know how big it is. I want to know how heavy it is. I want to know, you know, what shape is it? All these kinds of questions. And so these kinds of things about like, well, what are these objects like? That's what we are going to use to solve, you know, we're not going to solve all of planet formation tonight. We're going to kind of focus in on, well, how do these little planetesimals form? The problem comes, and these were major challenges 10 years ago. There's an unsolved problem as of 10 years ago, now more solved, as we'll talk about later. But the major problem comes, because, you know, as I mentioned before, you start out with this big cloud of gas and dust. And really, when I say dust, I mean the finest particles, finer than cigarette smoke, finer than talc powder, really, really tiny dust pieces. And you need to turn those into, 1 mile wide rocks, right? So how do you do that? And we think that it's kind of a bottom-up process. You start with 1 and you stick those together. Now you have a little 2 and you take 2 and 2 and make 4 and so on. You kind of build all the way up. And you might think about, so a great analogy for this in our everyday lives is a dust bunny, right? So these little collections of dust that happen, if you underneath your bed and say it's a hardwood floor, and the dust collects under there and it kind of collects into these big clumps, right? Perfect. But from personal experience that if I take 2 of these dust bunny clumps and no matter how slowly I try to put them together, I'm not going to make a boulder, right? I'm not going to be able to just keep putting dust bunnies together and throwing them at each other in space and having them stick together and become a boulder. That's the simulation here is a simulation of that. And people have tried. People tried to take bigger and bigger dust bunnies, and you eventually get to something called the bouncing barrier, which is once you get out to about the size of a centimeter, about an inch in size, when you try to stick 2 things together, they might kind of stick, but then half of it flies off in little pieces and you can't do it, right? And maybe they're not dust bunnies, maybe they're a little bit harder, but that's even worse, right? I've never gotten 2 pebbles to stick by throwing them at each other, right? No matter how slowly I do it, this doesn't work. And so it doesn't work. So that's a problem. The other problem is, suppose somehow you get things to stick together and you make them about meter size, so about as big as a person. Well, when that happens, the short version of the story is there's all this gas around still. There's all this air around. And this big fluffy object or hard object, whether it's a boulder, doesn't matter too much, it turns out it's flying through this gas. And there's drag, there's gas drag, there's friction. And this process takes objects when you have something the size of a meter, and the friction is so strong that it will drag it all the way into the sun. And this will happen in like 100 years. And that's like 0 time for an astronomer thinking about planet formation, because it's like, so every time you make something that's a meter, it's gone. And so how do I make something that's a mile high if every time I make something that's a meter, it falls into the sun? When I've been teaching planetary science for a long time, around 2010 or even into 2015, I would tell this to my students and say, literally right now, the answer is magic. And now we have planetesimals and we keep going. I keep telling the story. Okay. Now I have a kilometer. Once you have kilometer-sized objects, then their gravity starts becoming important. And then, it kind of makes sense that they start accumulating into bigger planets. But getting up, at this size, if I have dust bunnies in space, gravity is not pulling them together. It has no effect. And so this was a big problem. I'm going to answer how this problem. I'm going to answer this problem while I talk about objects in the outer solar system, because they kind of go together. I see there's a question. I didn't look at it here.
Yeah, it's he wanted to comment, ask you to comment on the formation of the atmosphere of the planets, how and when that comes along in the process. So that's from Chris Harness.
Yeah, let me mention that now. Now's a good time to get into that. We have 2 different kinds of planets in the solar system. Planets with huge atmospheres like Jupiter. Jupiter's mostly atmosphere, depending exactly on how you define atmosphere. But Jupiter is mostly made out of hydrogen and helium gas. And then we have planets like the Earth, which despite the fact that I'm breathing right now, I will say have no atmosphere. And the reason for that is, especially for an orbit sky, I think about how heavy something is. The heavier it is, the more important it is. If you take the whole Earth and you take the atmosphere and you see, well, how much of the weight of the Earth is the atmosphere? It's less than a millionth. Right. So 99.999% of the Earth is rock and metal and not even water, a little bit of water, but and basically no air. And so you have planets with no air, terrestrial planets, and then you have planets that are mostly air. And the short version of that is all the planets are growing. They're growing in this process, and gravity's kind of helping them to grow. When they get really big, their gravity becomes so strong that they can start vacuuming up, sucking up the gas that's also floating around. The gas is always there. And the gas is the dominant component, mostly gas and then a little bit of rocks and ice here and there, a couple percent. And so if you get really big and you can start gathering the gas, well, then you get more massive, and then you can start gathering more gas and you get more massive, and you start from something maybe 5 times as massive as the Earth, Jupiter, maybe 5, maybe 10 times as massive as the Earth. And then it just grabs now 300 Earth masses of material to make this huge gas giant planet. And we think what happened in our solar system is either you got big enough to just grab everything, or you didn't. And if you didn't, you end up like the Earth. And if you do, you end up like Jupiter. And we can maybe talk more later if people want about, well, why was Jupiter so special and the Earth not, and things like that. That's a kind of a different thread that maybe we can talk about later. Okay, but we've got this problem. I can't take dust bunnies and I can't stick them together. And if I do, they'll fall into the sun. So this is a problem. All right. Well, how are we going to learn? How are we going to figure out the answer to this problem? Well, we can look around. We can look at we saw some beautiful, I was really enjoying the astrophotography pictures that you were showing, beautiful pictures of gas clouds in space. And we can study those. And if you zoom in on those, sometimes you can see these little planet disks, these disks that are forming planets. Let's try to study those. What some people do is they start with, okay, I have the solar system now. So what was the dust like way back then? That's really hard, but you can learn a little bit about what was happening back then based on the final result that we see now. In our own solar system, you can do that with the planets, for example. Really valuable in our solar systems, we have meteorites, and so you can literally crack one of these open and take a look inside and see what they're like. We learn a lot that way. But we also have small bodies, lots and lots of asteroids, right? And they're floating around, and the way that they orbit the sun and their sizes and things like that, it's telling you something about planet formation, right? There aren't asteroids everywhere. There are only asteroids at certain places. Some asteroids have more rock and other asteroids have more ice. Well, that's telling you something about where the rocks were and where the ice was and things like that. So that's a great way to go. And the other way you can come about it is taking what we already know and really trying to study the physical processes, the physics, the astronomy, the planetary science. And the real challenge of planet formation, why we haven't solved this problem already, is that planet formation is a very complex problem. Lots of moving parts. There's chemical reactions that are happening on the dust grains. There's gas and different kinds of gas and different kinds of dust and electric fields and magnetism, and everything spiraling into the sun. And it can be a really complex problem. But we know a lot about the pieces. So as we get better at saying, well, this is what magnetic fields do to the disk, and this is what this happens, we can get more and more sense for that. So we could do more detailed studies of these observations. This is kind of the ways that we can make progress. All right, now let's take a look at the outer solar system, because it's going to really help us with this. This is a animation. You might be able to see the little white dots showing up on your screen. This is an animation of the discovery of the objects in the outer solar system. So the gray circles that are easily seen are, there's some little ones on the inside, and then Jupiter, Saturn, Uranus, and Neptune. And these dots, as they show up, are showing the discovery of objects out beyond Neptune. And if we actually tilt the diagram, look along the edge, you can see the planets are very flat. They form this very flat ring. But these objects, some are way out of the plane of the solar system, high places. Some of them are bigger than others. And you can also see that there's, a couple thousand of these objects that have been discovered. The first of these Kuiper Belt objects was Pluto, discovered in 1930. In a variety of ways, a happy accident that it happened to be discovered, 60 years before the next object out there. But then once in 1992, it started to become possible to see some of these, then it kept more and more people were looking, and now there's about 4,000 of these objects that are known. They're really hard to find because they're really far away. And we see them from reflected sunlight. So the sunlight has to go way out, 50 times further away from the sun than the Earth is, and hit this little ice ball. And then that light has to come way back and hit our telescopes here. And so they're very faint. WASP might be able to see Pluto. Pluto is about 15th magnitude, but it's really tough to do without a bigger telescope or thing like that. And actually, really what happened in the 90s that really made this possible was the switch from photographic plates to digital detectors, CCDs, cameras, basically, which the reason everyone now has a camera in their phone is because astronomers wanted to get better pictures, 50 years ago. And so this allowed for this. All right, so we have these ice balls. They're way out in the outer solar system. And so they are made out of mostly ice with some rock, about half ice, half rock. So different from the asteroid belt in that way. And also, because they're so far away and they're really hard to see, we can only see really big objects. And I mean big. These biggest objects that you're seeing on the screen here, we call them dwarf planets. There's Pluto and Eris and Haumea, Makemake, and some others possible. But each of those objects is as massive as the entire asteroid belt put together. Right? So Pluto is more massive than the whole asteroid belt. And so these are big, bigger objects, bigger, icier objects. And they're telling us something about the way that the planets form. All right, so I'm gonna have some charts in here, some graphs. But we'll kind of go through them, make sure we understand what's going on. And this is now a diagram I told you before. The thing that we learn when we learn about an object, we learn how it's orbiting the sun. That's the main thing that we learn. So this is a diagram that's showing 3 of the most important parts of how an object goes around the sun. So here on the horizontal axis, we have something called semi-major axis. That's the size of the orbit, how big the orbit is. And it's measured in AU, this is astronomical units. The Earth has a semi-major axis of 1 AU. So this is telling you that these objects that we see out here, they're 40 to 50 times further away from the sun than the Earth is. Okay, so in these big orbits. On the vertical axis here, we have perihelion, which means how close, what's the closest, when that thing is orbiting around, what's the closest that it gets to the sun ever as it goes around in this big orbit? And that will be important as well. Here, I'll explain one reason why it's important. If you get to about 35 AU away from the sun, down here at 30 AU is Neptune. And it's way more massive. I mean, these guys are as big as the asteroid belt, but Neptune is as big as like 10,000 asteroid belts. So if you get even close to Neptune, if you get to sort of 35 here, then Neptune will start pulling you around and you go on an unstable orbit. And so objects below this line, they won't last. They disappear. They actually become comets. If you get too close to Neptune, then you can end up becoming a comet. But if you're above this line, you're pretty much safe. Which tells you that these objects that are here, they've been here for a long time. Neptune can't pull them out, but that also means that Neptune can't push them in. So these objects here are kind of away from Neptune. Let's talk about this line here. This line is when you have a circular orbit. And that makes sense because we're saying, okay, the size of your orbit, kind of like the radius of your orbit, is 41 AU. The closest you can get if you're at a circular orbit is 41 AU. You can't get, if your circle is 41 AU, you can't have the closest to the sun be 45 AU, right? That doesn't work. So this line here is circular. So the closer you are to this line, the more circular your orbit is, which means that this vertical direction is also giving you a sense of how ovally, right, how elliptical the orbit is. The shape of the orbit is also okay. And then the colors. What are the colors showing? The colors they're divided into 3 categories, and this is the tilt of the orbit relative to the plane of that solar system that I showed you before. So all the planets have almost perfectly untilted orbits to within a degree or so. And we've colored these triangles. Every triangle here represents a single Kuiper Belt object that's been discovered. And we've colored these triangles based on whether they are pretty untilted, these red triangles, a little bit tilted, 5 degrees, not too much, or quite tilted, more than 10 degrees. All right, so this is from a recent review paper that really was trying to put all this information together and kind of present it. There's a few other things on this plot that we don't really need to know about. But if you look at this plot, at these objects that have been discovered, it becomes pretty clear that there's some interesting things going on. First of all, there's more than one kind of orbit, right? We have some objects that are close to the sun and tilted. We have some objects that are far away from the sun and untilted. So we definitely have different things going on. And in particular, we have this clump right here, right? You can see it immediately. As soon as you see this graph, you see, okay, there's a clump, there's a lot of objects here, and they're all on these untilted orbits. They have low, so sorry, I forgot to change on my slide here. Inclination just means tilt. So these objects are untilted, they're near circular, and it turns out they're also smaller. These are the whenever we find a big object, it's never in this area. It's always out in this. It's never in this purple area. The big objects are all out here, and we never find big objects in. We have other evidence from various lines that I'm not going to talk about, that these objects that are right here, they formed right here and never moved. And that makes this group of objects the most pristine planetesimals in the solar system. These are in deep freeze. They formed there, they never moved. Everything else in the solar system, asteroids, all that, those have all moved around and gone up and down. These objects are also so cold that they never melted. They form in some planetesimal formation process, and then they stay that way for 4.5 billion years until today. And so these objects, if we want to know, well, how do you bring objects together? How do you get things to stick? What's the process by which this happens? This is your population that you want to understand, these cold classicals. Oh, yeah, these are called cold classicals. We'll just say they're called cold classicals. I won't. Sorry. Okay, hold on. Okay, this way. All right, cold classicals. So there's this. Not all the objects out past Neptune, but there's a subset of objects out past Neptune that are pristine planetesimals. They just formed right out of the solar system. Okay, cool. And I like to kind of pause at this point. I'd like to show you your seat in this diagram. I know you all aren't at the observatory, but this is our cosmic address, right? This is where we really live. These objects that I'm talking about, they are real ice balls that are our real neighbors, right? I guess maybe not neighbors as much as Mars and the asteroid belt, they're a lot further away. But, I mean, if you zoomed in on this diagram, you could zoom in all the way to where you're sitting, right? This is our solar system. And so it's fun. I study planets around other stars and they're really cool, and aliens and all that. And that's all really fun too. But there's something special about, like, this is our neighborhood, right? This is where, we're in the outskirts, but we're really exploring our own things. And I really like that. Now, what we'd like to have is pictures like this of these objects, right? We like to take the 14-inch, right, and zoom in on Pluto and get a picture like this. Well, you can't do that. It's too far away, and they're too small. And so NASA took $1 billion of your taxpayer dollars and sent the spacecraft there. In this illustration, I put the spacecraft there. The spacecraft is taking the picture. It can't also be in the picture, but that's just to give you a visualization. This is a real picture of Pluto taken from the spacecraft. And I really like this one because this is like, if you were like in an airplane, like flying over Pluto, like you're flying from one part of Pluto to another, and you're on a domestic Pluto flight, and you look out the window, this is kind of what it would look like. And it's really, and this is one of the most interesting parts of Pluto, but there's we could have a whole, in fact, you should probably someday have a whole talk on this. There's nitrogen glaciers, there's water ice mountains, this fuzzy, these layers in the air up here. Pluto does have air, just a little teeny tiny bit. And these layers are actually real. Those are real. All these lines. How do you have nitrogen glaciers and lots of really interesting stuff going on. This is what we'd like, but Pluto is not a cold classical, right? So it's not a pristine piece of the solar system that formed. It formed kind of like the planets did. You get a bunch of ice balls together and and it gets big enough and it melts and turns into a sphere and all those things. So Pluto is great, but it's not a cold classical. Instead, what we usually get is pictures like this. This is a picture. We use, one of the telescopes that we use here at BYU is the 3.5 meter telescope in New Mexico at Apache Point, called the Astrophysical, we're part of the Astrophysical Research Consortium. And this is a picture that one of my students took. You can see there's lots of fuzz. That's actually an animation of a sequence of images. And what you see is stars, and then one of these stars is moving. And that's because that's not a star. The object that's moving is one of these Kuiper Belt objects in the outer solar system. And so, so this is how we find them, as we track these, we take pictures of the same part of the sky and watch for the dots that move. And you would just love to okay, we'll just like in the movies, like zoom in, like enhance, right? And then it comes out, but that's not how it really works. So we can't do that. But if we could enhance by, say, taking a picture with, I don't know, whatever telescope you happen to have around, maybe the Hubble Space Telescope, right? So you have a Hubble Space Telescope, and your taxpayer dollars are paying for it to take $100,000 picture. You take a picture of this object, and you would actually find out that this object isn't one object. It has a moon, or a binary. Actually, the two components are pretty similar in size, unlike Jupiter and like tiny Io, right? You were talking about seeing Enceladus earlier. Enceladus is nothing compared to Saturn, right? But these objects are actually pretty similar in size. And then if you use digital enhancing techniques on the Hubble Space Telescope images, and you really zoom in, you actually find out that you actually take a look at this middle object, and you can actually just barely tell that this is actually two objects, similar brightness. And it's at the level where with your eye, I can convince you because I put the 1 and the 2 here, and you might believe me because I'm a scientist or something like that. But really you need a computer to model it and things like that. The nice thing about Hubble's, there's no air, right? So when you take a picture, you almost know exactly what you're getting. So it's fantastic. And these are, for those who are familiar with sky coordinates, these two objects are separated by only 1/10 of an arc second. And they're really faint. These are 20th magnitude objects. So 2/20th magnitude objects separated by 1/10 of an arc second. That's what the Hubble Space Telescope is good at. So
is there a chance that you could have the James Webb Space Telescope look at this too? Because I think the resolution would be even better. Infrared. Is that something that's on the docket?
Yeah, it's a great question. So it turns out that infrared is actually worse for distinguishing features, for like telling two objects apart. And the short version for that is, the reason that things kind of get blurred together is
heat, I'm sure. Two warm objects next to each other.
So for Hubble, the reason that, why when you take a picture with Hubble do you not just get, because the actual size of these objects is way smaller than the blob that I'm showing you, maybe 1,000 times smaller. Well, then why don't I see like two little teeny tiny dots? Well, the light from those dots has to go through the telescope, and light, despite astronomers' best efforts, is a wave, and the wave just you can't squeeze it. If you try to squeeze it one way, it just squishes out another way. And so you get your telescope, when you get your telescope aligned and perfectly polished and the right shape and everything's just right, you're trying to get the best that you can in the squeezing of the light. But you actually you can never squeeze it down all the way. And how wavy light is and how easy it is to squeeze down depends on the wavelength of the light, the color of the light. And infrared light is even harder to squeeze because it's bigger waves. So it's like bigger. And so James Webb is actually, so, but if you have a bigger telescope, you can squeeze more. So James Webb is a much bigger telescope than Hubble, but it's using light that's less squeezable. And so that actually turns out to be about even. But James Webb does have like one camera on it that can do like regular normal light, not infrared light, but visible light, red visible light. And so we thought about doing that. We asked James Webb Space Telescope to look at this object because it has a really interesting, there's lots of interesting orbit stuff going on. I'll jump to the surprise on this object, which is we've solved for the orbits of these objects and they are impossible. Oh, good, right? So that's a perfect telescope proposal. They're impossible because the way the orbits work is this system should have disintegrated, within the last, the time it takes for it to totally just like blow itself apart is about 10,000 years, but we think it's, over 1 billion years old. So how can that be? And the only way we'll find out is if you give us some James Webb Space Telescope time. And we tried and they said no, right? So we'll try again. There's another James Webb Telescope proposal set due in October. So I think we'll try again. And if we do, I think, yes, you're right. And we'll try to do the one where we can really see what's going on. It won't be way better than this, but it will be nice. Actually, quick aside, this is actually Hubble's best camera that it ever had for distinguishing things that broke back in 2005 and we haven't had since. So we actually couldn't even take this picture with Hubble now, even if we wanted to. And so that's what we told the telescope committee and they still said no, but we'll try again. But anyway, let's go back to this object. So this is cool, right? Because we have now an object. It's actually there's actually three ice balls, two orbiting around each other, kind of a little orbit, and then another moon going around the two, right? Which is really interesting configuration. It's actually the only one in the solar system that's quite like that. And here's kind of this in the lower left here is this animation of how we think this works. And this was discovered back in 2010 that there's three of these objects going together. But the problem when you have three objects is that now tracking them becomes a lot harder. Well, actually, tracking them is still as easy. So the way this works, what did we do? We use the Hubble Space Telescope and we take a picture. And when we take that picture, we're like, okay, this object's here, this one's here, and this one's here. We come back a couple of days later, and now they've all moved. Okay, and we come back a couple of days later again, and now they've all moved. And then literally a good fraction of my PhD was connecting the dots, right? So it was here, then here, then here, then here. And now, you draw an ellipse and there they all are, right? It's a little bit more complicated than that. So there's only two objects and some other, the simplest case is that there's only two objects. And then if you took an astronomy class, one of the things you probably learned is there's these things called Kepler's laws that talk about how objects move around. And one of Kepler's laws is that objects move in ellipses, ovals. There's a very particular shape that they follow. However, that only works if you have two perfect objects orbiting each other. As soon as you have three, they don't follow these oval patterns anymore. And you can see if you're really a sleuth here on the lower right. Basically, you can see we tried to draw an oval that went through all of the observations, but we couldn't do it, right? There isn't one oval that actually works. And this is totally expected because you only get ellipses if there's two objects, but there's three, right? And when there's three, then they're kind of like ovals, but they're like moving ovals. And so it's like, oh, okay. So it's a lot harder to do. And actually hard enough and kind of beyond the capability of a lot of people. So I love orbits. And so I was like, ooh, three objects? Let's do it. Everyone else was like, no, I'm good with what we've got. So we were able to finally solve this system, not by using two ovals, but by using the actual full, this object's pulling on that out. All three objects are pulling on all of each other's objects all at the same time, and then making that all, getting all the pullings and pushings and the sizes all lined up so that we actually get all the data points that have been observed. So we were the first group to solve the full three body, we call it three objects. Okay, well, this is a really interesting object, LIMPO, but there are others that are also really interesting. It turns out there's about 100 of these objects where you have the two objects going around each other. And I'd like to keep moving forward real quick and get to now thinking about simpler objects where I just have two going around each other. And one of the key questions you can ask is, okay, I've got these two objects going around each other. What's the orientation of how they go around each other, right? Because they're also going around the sun. So you have a couple options. You can go around and kind of this, say you're looking down on it from the top, and so you're orbiting the sun counterclockwise, and the two objects also go around each other counterclockwise. That's on the left part of the diagram here. You could have that's going around counterclockwise, and these two objects are sideways, like Uranus is, for those who are familiar with that. That would be 90 here. Or you can have them that they're going backwards, right? I have two objects, they're going around the sun counterclockwise, but they're going around each other clockwise. We call that retrograde, right? So back, kind of going backwards in a sense. So they both move together around the sun, but then how do they move kind of with the way that they move around the sun or against the way that they move? And this is the actual answer for many of these objects. You can see that a lot of them go the same way. Some of them are sideways, some of them go backwards. And exactly how they go around turned out to be really important for and to be a key clue for how planetesimals form. And so let's talk about that. So I told you earlier, you have these little dust things and they're trying to stick together and it doesn't work. And so when they did a more detailed calculation of not just dust, but also gas, something new happens when you do the gas and the dust together. And you can see in this video here, you get clumping. And what's happening? Well, it's basically the same phenomenon that happened, when I have a particle moving in the gas, it makes a wake. And that wake attracts other particles, it turns out. And then they make wakes and that attracts more particles. And so you get kind of this like geese flying in a V formation kind of thing where you actually tend to clump these particles together, not because they're sticking to each other. So they're not sticking to each other. They're just kind of flying together. But then eventually, if you get, you get a billion dust bunnies and they're all flying together and they're all close enough together, eventually their gravity will just bring them together and they will just collapse and turn into an object directly. So you start from dust bunnies and go straight to 100-mile size objects made up of a bajillion dust bunnies, collapsing. And we actually think this is now, and notice that this gets past the problems I said before. They don't have to stick together, and they never are in this size where they fall into the sun. They go straight from the dust bunnies that I know how to make to the objects that we see today. This is called the streaming instability model of planet formation. We think this is how you do it. You get these clumps. And when these clumps happen, then you can switch to another model that takes these clumps and actually sees, well, what happens to all the pieces that are in these clumps? So I have all these pieces that are in these clumps, and now this big pile of dust bunnies collapses. And what happens? Well, they don't all just fall into one perfect object and form a single object. They fall, and then some of them miss, and then some of them fly around, and you have lots of different kinds of things flying around. And it turns out that because whenever you start with something big, and then you shrink it down, you have to what's called conserve angular momentum, and it's pretty easy. In fact, it's very common when this object collapses. It doesn't collapse into a single object; it collapses into a binary. It collapses into two objects orbiting each other, often about the same size. And when we look at this process, we do this animation that I showed you. You do it, 1,000 different times for different configurations, and you see, well, what kinds of binaries can I make from this? I start with this clump that I made in the last diagram, and now I let it collapse and see what happens, and I make binaries. And what happens? And one particular question you can ask is, what's the orientation of these binaries? Do they orbit the same way that they go around the sun? Do they orbit backwards? What's the answer? And the answer was about 80% of them should be going with the way they go around the sun. 20% should be going backwards. And lo and behold, here's the plot that came from the observers. So there's this really nice synergy between, and the computer simulations were now strong enough to tell us what we should see. And at the same time, we had these observations, and this is a really, really powerful match. In fact, I would say, now this model for planet formation, the streaming instability thing, they're using it to make planets run other stars. They're using it all over. And this is probably the best direct evidence that we have, because again, these objects formed in these binaries and have been and sat there for 4 billion years. And so now we're coming around and looking at them and saying, ooh, you're orbiting sideways. Okay, that tells us something about the process that formed these planetesimals. So that's really fun. I said before, we'd love to have a picture of one of these cold classicals. Well, it turns out we do. That same telescope that flew past Pluto kept going, and we worked really hard to find a cold classical that it could also, kind of change its trajectory and fly by and take a picture of. So we actually have a picture of one of these cold classicals. This is Arrokoth, it's called. It's in the lower left is Comet 67P, which is a comet that was studied by a European Space Agency mission to scale, to see that this is like a mega comet. And, this isn't what I thought it would look like. It's really smooth. And in fact, it looks like this, like it might be a snowman, like two spheres, but it's actually not. It's two, not quite pancakes, but almost pancakes that are stuck together. And this seems really interesting, right? Especially, we're talking about binaries, right? You form these two objects, and then this is like you had a binary, and then you stuck the pieces together. Well, it turns out the streaming instability is good for that, because what do? You form this big cloud that I talked about. You form this binary, and the streaming instability requires gas, there to be leftover gas. And then the gas will, and then that same drag that I talked about before that was bad because it got rid of things, now it's like slowly slowing down this object until they are just barely orbiting each other, and then they kiss, and then they kind of stick, and they orbit this way. And it turns out that is the way it orbits. It orbits in that exact same sense that you would expect from this model. So this is around the same time as the other one. We got this other story that, wow, Arrokoth, how do I explain what it looks like? The streaming instability is a great story for this. Well, this is interesting to me because this is, this shape is really interesting, right? It's not a sphere. It's interesting to me because I study the orbits of these moons as they go around. Here I'm trying to connect the dots here. You can see that. And as we study the orbits of these moons going around, all we can see is where the moon is. And we can't zoom in on all these other objects like we can with Arrokoth. And so all we can see is where the moon is. But it turns out, kind of jump to the end, it turns out that the way that a moon orbits an object is different if it's a sphere or if it's a potato. So if I were to put a moon around Arrokoth, it would not orbit in a perfect oval. It would be an oval that's kind of changing, that's moving around. Let's see if I can show you that. And so we can measure how squished the object, we can measure the shape of the object by watching the moon. Because if you're orbiting around, this is an exaggerated picture, but if you're orbiting around something that's not a sphere, then the orbit kind of turns. We call this precession. The orbit changes the way it goes around. And you can imagine that if this what was happening on the left, if that was what was happening on the right, I would be able to tell, right? Because these circles, this is what I measured from Hubble. And so if I came back a few years later and now the now the orbit was this way, right? It would be easy, right? Because my where the dots are would be in a totally different place. So this tells us that we can measure this effect. We can actually measure and say how squished, how non-spherical is this object that the moon is going around. Eris, which is a very famous object in the outer solar system, because it's more massive than Pluto, Planet X, the whole thing. It has a moon, and we've been watching this moon, and this moon is not going around in an oval. And we think what's happening is that there's another moon inside of the known moon. But then you might say, well, why haven't we seen this moon? Well, remember that light squishes, light can't be squished down. And so it's probably in here in this fuzz ball and can't be seen. We can see this outer moon, but we can't see this inner moon. That's one cool result that we have. So we did this process where we looked at all the objects, and I had some sophomores help me, and we're going through and making these tables and writing these papers and doing all these things. And the short version is we find many objects that are not spheres, that are different shapes. We find big objects. We're finding that they're not spheres. We're measuring how squished they are. We're finding some objects that when we do our calculation of how squished they are, which is this, what's on this x-axis here, sort of J2 is this, how squished it is. These are so squished that they can't be one object. They actually have to be two objects. Remember the LEMPO one that was two going around and then another moon going around that? They must be like that, but now so close together that we can't see the two little ones. But by watching the moon really carefully, we can tell, oh yeah, this isn't one object. So if we now look at these cold classicals, right, these pristine objects, and now add in this piece of, well, what are their shapes like? No one's ever measured their shapes before. And here we are, we're measuring the shapes for the first time. And the answer is that the shapes, here's Arikoff's shape on this axis, really squished. They're all squished. Some of them so squished that they're probably two objects going around each other, as I mentioned before. And so this is interesting, right? Because we now have another piece of information that's telling us these objects are all squished. And it supports this streaming instability model, because when you have this big collapse and you have all this stuff that's flying around, and you saw it was flying around, kind of orbiting around each other, that tends to make squished things. And so this is a natural kind of connection, confirmation of this idea that you form these objects not by building them up piece by piece, which would tend to form spheres, by having this huge collapse all at once and all this material kind of flying around, making these elongated shapes that we detect in the data today by watching the moons really carefully. So hopefully, some fun things about how science proceeds and how we can answer questions. But it looks like we are really understanding now how planetesimals form. You get up to dust bunnies, but then you make huge objects all at once. And then you go from there to planets. So thank you everyone for listening. We talked today about planet formation and how it works, and how these pristine objects in the outer solar system, and especially the ones with moons, are really able to tell us new things about how planets formed, and kind of matching up with existing data. And we've been finding a lot of these fun things. We have students working on it. We have funding from NASA and NSF to try to figure out how these objects orbit, and what that means for how our solar system formed. So thank you, everyone, and I'll be glad to take some questions.
Well, I was in the spherical camp well before this. Now I'm in the non-spherical camp. So
good.
No, that was really interesting. I really didn't realize, even knowing and knowing what those objects look like recently, because we visited them, it just didn't occur to me about why or how they would form so differently other than a round object. So
yeah,
thanks for explaining that, because I did not understand that at all. We don't have a lot of questions at all, I think because we the Zoom panel did not work well. But can we get out there? Is there any other, how do we get out there and see this stuff? How do we get, what are the next plans to go out there and observe other objects?
Yeah. So I mentioned the spacecraft that went out there already, took pictures of Pluto and Arrokoth. That was the New Horizons spacecraft. It flew by Pluto in 2014, and it flew by Arrokoth in 2019.
Yeah, they changed the name of one of them.
Arrokoth was called Ultima Thule for.
That's right. Yeah, Arrokoth, that's it.
Yes. So, and that mission, first of all, was an incredible feat of engineering. I really think the engineers should get serious props for this. It was launched, took 13 years to get there, and arrived within 90 seconds of the goal. So, I mean, talk about a hole, this cosmic hole in one. But these objects were really far away. So New Horizons, which is basically one of the fastest things we've ever sent, took 13 years to get out there. And before that, it takes 13 years to decide to do it and to build it and to get the money, and NASA cancels it and then reinstate it. And so what this means is that if you want a picture of your favorite Kuiper Belt object with sort of the classical space exploration things, there are some novel ideas that maybe could do this. So you first go and you convince NASA to do it. And then it takes 25 years from that point to get the pictures back, because it takes 10 years to build it, 10 years for it to get there, and then it just takes a long time. Right now, there is nothing in the hopper, and in fact, probably not anything anytime soon. There's lots of things to explore in the solar system. So New Horizons kind of got their pick, and now the next. Probably, there's lots of things going on everywhere. There's a couple really cool Venus missions going. There's a mission to a metal asteroid. But to get out there, you also need a big budget, because it's a lot of work to get out there.
What about using something like a light sail, which is, something that is really, much more inexpensive to do, and trim it. You can move around with them.
It's quite plausible, I think, especially for this distant solar system region. I think it's plausible that one of these more newer technologies like a light sail, or there's some ion thrust engines that can be really powerful and things like that. It's possible that they may get to this outer part of the solar system first before NASA, decides to do it and then builds it and then takes 10 years to get out there. So I would say, because so it's not even on kind of the short list right now of things to do. So that means we've probably got 10 years before it'll even be in the beginning of this process. So, right now I would be surprised if we got pictures of another outer solar system object in the conventional way within the next 30 years. So, but unconventional is plausible, more fun, but unconventional, right? So it has its own challenges.
Yeah. Chris Hartnoff had asked another question too. Are any of the objects thought to be from outside the solar system by their orbit or composition? Something like Oumuamua, I'm sure he's referring to.
Yes, yeah. So I'm really familiar with Oumuamua. Oumuamua is an object, one of these, ice balls or asteroids. It's actually still debated today what it is, what it was. That was not orbiting the sun at all. It came from the galaxy. And literally flew in, kind of flew by the Earth. We took a few pictures, and now, it's on its way out of the solar system. So this is like a completely different kind of object than the things that we are looking at. And where does it come from? Well, we didn't talk about this part because we were mostly talking about planetesimal formation. After planetesimal formation, and you start making these big planets, those big planets have a lot of weight. And so if you fly by Jupiter the wrong way, Jupiter will kick you out of the solar system. And so the process of forming the solar system, we actually kicked out probably 1 trillion asteroids out into the galaxy. And presumably, so did everybody else, right? So all these other stars are out there, they're making planets, they're kicking out trillions. So if every star in the sky kicks out 1 trillion comets, then, there's comets out there. The galaxy is huge compared to the solar system, right? The volume of just the nearest star is like a million sort of times, bigger than let's do a billion. Not quite. No. A million, only a million times bigger. So the volumes are huge, and so you don't see very many of these objects. And the way that we could tell these objects are not from our solar system is they have a completely different way that they go around the sun, in that they don't go around the sun. They're not part of the sun's family. Yeah, they fly by and they never come back. And so the shape, I was showing you all these ovals. Ovals are if you're going around something. But if you're not going around something, and here's the sun, you end up with an orbit that looks like this. Well, I didn't try it very good. It's called a hyperbola. It's just a completely different kind of orbit, and that's it. And it goes out forever this way, and came in from this way. No ellipse, no nothing like that. And so when you find an object and you start tracking how it's moving around the sun, it doesn't take very long before you're like, oh, this is not going around the sun. This object's in a completely different shape of a trajectory, and that means it's not one of ours. So Oumuamua, and there's another one called Borisov that we found recently. We're hoping that a new telescope in Chile will find, another 10, 20, 30 of these objects over the next decade. They're very rare. But everything that's orbiting around the sun probably pretty much belongs to the sun. Some people were talking about maybe, oops, that's not what I wanted to do. Some people were saying, well, maybe you could, fly by the sun and somehow get captured and end up, in the sun. But it turns out that that's really, 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 really hard to do. So right now, everything's very clearly in the camp of, yep, comes from the sun, from our own solar system, or no, from a completely different part of the galaxy.
And Avi Loeb will call it probably something from an alien, when
for those travel stickers, Paris, Rigel, Alpha.
Yes. Well, the funny part of that story is, so right before Oumuamua was discovered, fortuitously, I wrote a paper about these objects. And actually, Avi was almost a co-author on that paper because I was building, I know I was at Harvard at the same time that I was working on this paper. And he ended up not being a co-author on this paper. And then, but I think he has been interested in these objects. I was building on a paper that he had already written with someone else. So he had been interested in these objects for a long time. And but yes, has a different view than the standard astronomer does about
that was a very genteel way to say that. And we had him as a speaker.
Oh, great, good.
Maybe about a year ago. So yeah, I mean, it's like, why does everything have to be an alien? But yeah, why is the person? I agree that you shouldn't rule it should always be that possibility.
Sure.
But, I guess
yeah,
it makes for good ink. He gets a lot of ink on it, and
so it's an interesting setup. So
well, on that note, I think I don't see any other questions. Anything else from the board?
Yeah. Can you comment a bit on the Grand Tack hypothesis about planetary formation?
Yes, sure. So right now, probably the leading model for planet formation, when you get all the way up to planets, I was focusing on making the small bodies today. When you get all the way up to planets, is something called the Grand Tack. And I mentioned before how Pluto is more massive than the whole asteroid belt put together. But Pluto is tiny compared to even the Earth. And so when you look at the space between Mars and Jupiter, you really get this sense that there's a lot of there should be a lot more stuff there, and there isn't. So what happened? And that, plus many other considerations, led to this model called the Grand Tack model, where Jupiter forms, and then there are processes. Actually, we learned about a lot of them from Kuiper Belt objects. We see in the Kuiper Belt objects signatures that the planets have moved. They were not always in the place that they were today. We know Neptune has moved a lot. Neptune used to be where Uranus is now. and has moved significantly. And so if you do this with Jupiter and you let Jupiter move into where the asteroid belt is now, it eats everything that's there. And then this idea of attacking is kind of like a sailboat attack. Then then Saturn forms, and that causes something to change. And then they both move back to their current positions, basically. And so this grand attack model predicts that, Jupiter used to be where the asteroid belt is now, and that's one reason why it's so empty. And it's still, I would say, sort of the leading model. It's been a little while, so I bet here in the next few years, about every 5 to 10 years, a new improved model comes out, and it's possible that the grand attack will get replaced, of course, as all scientific models do. They get better and better. Right now, it's still, I would say, kind of it's definitely the most fashionable planet formation model right now, and thought to be accurate. It still has a lot of things going for it.
Thank you.
Anything else from the panel?
For me.
Well, Dr. Ragozzine, thank you so much for joining us tonight. It's a pleasure. It was, I didn't know what to make of the talk when I was reading about it, and now I got a lot out of it. So I appreciate what you did and talking us through it, because thank you. And next month, that guy right there that's sitting with a kitchen behind him, Bob Meadows, is going to do the annual Stellafane talk. Tickets are selling out. I just want you to know right now that it is always standing room only there at the Bob Meadows Stellafane report. And that'll be live in the classroom. So we'll be there at the Westport Observatory. I just broke my pen. That'll be at the Westport Observatory on the 18th, I think, of next month, or thereabouts. There'll be emails that'll go off, but yeah, so we'll be at Stellafane this weekend. It should be a great one. Don't forget, CSP is coming up too, and thank you to Franco for booking Dr. Ragozzine today, because I'm glad he did, and Franco's done such a bang-up job on getting great speakers like you. So thank you for joining us. Thank you for everything. Thank you for everybody that found us on Zoom and YouTube.
Hopefully after this talk, we'll have a little more appreciation and interest in possibly getting that moon next month.
Yes.
Dr. Kevin Green.
Yep, that's right. So that is
right in there.
Yeah.
We'll have all that stuff up too on YouTube on how to, to prepare for this, and how you can do it at home and someplace around Connecticut and Massachusetts, and really through the line. So thanks to everybody that joined us again, and we'll see you next month at the Bob Meadows Stellafane Report. Cheers, everybody.
Thank you.
Thank you.
Thanks, Doc.
Right.